Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 20 in the course Advanced Robotics. In the last class we talked about actuators and then we briefly started the topic of basic control systems. Today we'll talk about linear control systems and then we'll see how to design very simple controllers like PD controllers, PID controllers to control robot manipulators to take the end effector from one point to another point in space or to perform different tasks. Okay, so today we talk about linear control systems. And please note that we are saying linear control system. So linear control systems can be used for cases where the system being studied can be modeled mathematically by using linear differential equations. Okay, for such systems we can apply linear control system theory, and we are basically going to concentrate on linear control systems. Okay, so definition of a control system, very briefly going through what we had talked about in the last class. We said that definition of a control system is finding a suitable input to get a desired output. Okay, so that is the basic function of a control system. So we have a system like this and we are trying to find out what should be the input that to get a desired output. Okay, so that is the basic definition of a control system. Now again, we are in the last class we talked about a single input single output system. So we have a system in which we have the controller here and we have the comparator. Then we can have the motor. So this is my controller. We have motor. Then we have the plant or the robot. In our case it's a robot link, and there is a feedback, there is a sensor. Okay, so this is what we call a closed loop control system, and this is a single input single output, meaning there is a single input and and we have a single output, so there is only one output. Now we can also have a multi-input and multi-output system. So these are called single input single output systems. We can also have multi-input which are called multi-input multi-output systems, in which you have multiple inputs which are going into the system and there are multiple outputs which are coming out of the system. Okay, now robot control basically falls in this category. Okay, but we are going to simplify things and we'll make the assumption that we are going to design a control system which is a single input single output system for simplicity. Okay, but in reality a robot system is a multi-input multi-output system. Now why? Let's try to understand a little bit. We have studied dynamics, and in dynamics we did find that you have the propagation of velocities which are going from, so velocities and accelerations move in the outward direction from the base link to the end effector, and the forces move from the end effector towards the base link. Okay, so this means that every link affects the other link. So here every link affects the other links, or in a way the links are coupled. So this basically means that even if this link here is not moving, so this link let's say theta dot is equal to 0, it's not moving, but because the previous links are moving, this will be subjected to both linear and angular accelerations, which are going to cause inertia forces. Okay, now this means that the links are coupled, and we have our dynamic equation, which is tau is equal to m theta theta double dot plus v theta theta dot plus g theta. Okay, this is our dynamic equation. Now this is basically telling us that this is a non-linear differential equation. This is a non-linear differential equation. Okay, so first of all, it's a non-linear differential equation which is governing this. Second of all, this is a coupled system, which means that every link is affecting the other link. So in reality, it is not a single input single output system. Now what is this dynamics doing? So if you're trying to model the manipulator using a single input single output system, and also saying that each joint is being controlled by an independent joint control system, independent joint control, strategy. That means there is one motor, there is an encoder, and there is a gear in front, and every joint is being controlled independently. Okay, so suppose I want to move this joint by 30 degrees. Suppose I want to move this by 30 degrees. Only joint 1 will be actuated to move from whatever position to 30 degrees. So joint 2 and joint 3 are independent and they are not affected by joint 1. Whereas in reality, when it is moving, what will happen is the subsequent joints will also be affected by the motion of the previous joint. So dynamics basically, what does dynamics do? Dynamics basically acts as a disturbance. So in this particular case, I gave the example that the link has to move from here to here. Okay, so the link has to move from here to here. That means theta 1 moves by 30 degrees. Okay, so theta 2 and theta 3 are equal to 0. They don't move. Okay, in this case, what is going to happen is, because only joint 1 is moving by 30 degrees, the joint 2 and joint 3 will also be subjected to torques, inertia, Coriolis centrifugal, and gravity forces. Okay, but the controller, because it is independent joint control, the controller is only giving an input to joint 1, not to joint 2 and joint 3, because joint 2 and joint 3 are not moving. Okay, so this basically means that this dynamics, which is coming from joint because of the motion of joint 1, which is affecting joint 2 and joint 3, is acting as a disturbance on the system now. So in reality, if I go back to the control system diagram here, okay, there is going to be a disturbance which is going to come inside. So there is going to be a disturbance torque which is coming from here. So this is a disturbance now. This is my tau. Okay, so we have two inputs. You can see one input here. This is my first input, and there is another input there which is coming, which is the disturbance on the system. And this is what makes robot control very, very difficult. Okay, so because we are modeling this as a single input, single output system, and then proceeding with our analysis. Okay, so please keep this in mind, that the dynamics is essentially, or the effect of the dynamics is basically to turn up as a disturbance on the control system. And because we are making all this assumption that it's a linear system, okay, whereas in reality it's a non-linear system. Second is that there is no coupling between the joints, where in reality there is coupling between the joints. So these two assumptions make life difficult for the controller. But why do we make the assumptions? To simplify matters, so that we are able to do analysis much in an easier way. Okay, so let's proceed. So this basically says that I just tried to explain that why robot control is difficult, and in reality what it is, and we are assuming that it's a linear control system. So it's a linear control of manipulators. Okay, so although this is an assumption that we are making. Now, if you're saying linear control, we said that if the system being studied can be modeled mathematically by linear differential equations, then it's okay. Okay, in that case, we apply linear control theory. But in reality, this is not. But we assume and we say that we are treating this as a linear control system. Okay. Now we know that tau is equal to m theta double dot, okay, plus v into theta dot plus g into theta. Okay, this is the dynamic equation. Okay. Now we can have a open loop kind of control type of control. We can propose an open loop type of control in which we can compute the joint trajectories. So we can compute joint trajectories. So I compute my trajectory. We have learned how to compute trajectories by using third order polynomial. So the trajectory generator, let me give this example that the manipulator has to move from here to here. So it's at that position, it has to move to some other position. Let's say the manipulator has to move this side now, like that. So this joint is going from here to here, this joint is moving, and that joint is also moving. Okay, so I can say that at point A and I want to go to point B, I can find what is theta 1, theta 2, theta 3 at point A, and I can find theta 1, theta 2, and theta 3 at point B. Okay, so for each of the theta 1, theta 2, and theta 3, I can fit cubic polynomials. I put cubic polynomials. Okay, and then I have a trajectory generator. So the trajectory generator, basically what it does, it generates the theta d, then theta d dot, and theta d double dot. So position, velocity, acceleration I can generate from my trajectory generator. So this is my trajectory generator. This goes into the control system, let's say, control system, and the control system provides the torque using this equation. Okay, so it takes this and feeds it to the dynamic equation and gets the torque that is required at the joints. So the torque is given to the robot, okay, and the robot moves, and it takes feedback in terms of, let's say there is one feedback here, another one here, in terms of theta and theta dot. So this could be one way of controlling a robot, in which I want this robot, this is the example I've given here. It wants to move from point A to point B. The end effector has to move. Now to do that, all the joints will have to move, and we can find what is the position, what is the joint angles at position A and the joint angles at position B. Okay, and then the controller basically has to move the joint angle. Okay, so from angle 1 will go from theta 1 to theta 1 desired. Okay, so it knows, the controller knows it has to move by this much angle. So it will simply change the angles for theta 1, theta 2 and theta 3 until we have gone to point 2. And using trajectory generation, I model each of the joint angles, theta 1, theta 2, theta 3 by cubic splines. And from the cubic spline for each trajectory, I can find out what is theta d dot and theta d double dot. That means position, velocity, acceleration. I feed this to the control system. The control system uses this dynamic equation, finds the torque, and then drives the motor. Okay, so this is basically torque control. This is what we call torque control. Now the question that comes up here is, this looks like a realistic, doable kind of thing. The question is, this is an open loop. Okay, this is an open loop because this is not verifying what the trajectory was actually wanted. It is simply computing the trajectory, finding the torques, and the torque of the joint is being controlled. Okay, so it is open loop because there is no feedback here. There is no feedback to the trajectory generator. So we basically don't know what trajectory it took. Okay, will this system work? The question is, will this work? Okay, because it appears here that you can actually find position, velocity, accelerations, feed it to the dynamic equation, and then control the robot. But will this work? Now in reality, this will not work. Why? Because when we are making our dynamic equation, in the dynamic equation, okay, there are these terms M, V, G, and these are there are approximations involved. What do you mean by that? When you look at a robot, for example, I have independent joint control. So I have a motor, I have a gear, I have an encoder. Okay, so the exact inertia matrix, is not possible to obtain, because you may know the link the shape of the link, but in the link there will be screws, nuts, bolts, there is a motor which is fitted, there is a gearbox which is there. You will not know the exact inertia of those parameters. It's not possible to find. Okay, so it basically means that this would be approximate in some way. Now if it is approximate, then obviously your torque calculation is not exact. Now if it is not exact, then obviously you don't have an exact trajectory, and it's an open loop system. So it does appear that it's that this control structure will work, but in reality it will not work. Okay, because of the errors which are involved in estimation of inertia parameters, Coriolis, centrifugal, and sometimes gravity components, because the link parameters are not known exactly. Okay, and the manufacturer doesn't tell, and you cannot find them out. So if this structure is not possible, then what we basically do is we try and use a closed, that is an open loop system. So we don't use an open loop system, we try and have a closed loop system. Okay, so we have a closed loop system in which we generate an error. So we basically control positions. We do not control the torque, we control positions, and make the servo error go to 0. Okay, what this basically means is that we generate an error. So let me take the example of one link only. It is going from here to here. The same thing applies for all links. Now let me take two links. So there is one link here, and there is another link here. 1 degree of freedom, 2 degree of freedom. So this is my theta 1, this is my theta 2. Okay, now suppose I'm in this position, I want to go to the other position which is indicated here. Okay, so I have theta 1, it it is going from theta 1 to theta 1 dashed, and theta 2 is going from theta 2 to theta 2 dashed. Okay, so that's my theta 2. That's my theta 2 dashed. Sorry, this is my theta 1 dashed. This is my theta 1 dashed, and this is my theta 2 dashed. Okay, so basically what I'm saying is that there are 2 degrees of freedom, 2 angles, and the angles are moving like this. From theta 1 will go to theta 1 dashed. So what the controller does is it will find an error. It will create an error, which means theta 1 dash minus theta 1. It will create del theta 1, and then theta 2 dash minus theta 2. It will create del theta 2 as an error. Okay. Then what it will do is it will move the joint theta 1 towards this direction and theta 2 towards this direction, so that this error is going towards 0. Okay, this is what it means. Now this creation of an error and driving it to 0 is basically what we call by servo control, closed loop servo control. Okay. Closed loop servo control means you generate an error, means I am at what is this error? The desired position minus the present position, and drive that error to 0. So basically it means you are servoing, and that is what this is how it operates. Okay, it operates a single input single output system in servo control mode. So we are basically in the position domain, okay, not in the force domain or torque domain. In the previous, what are we controlling here? We're controlling torque. And how did we get this torque? We are getting the torque from using the dynamic equation. Okay, and we are seeing that this is not possible because there are a lot of errors which are involved here in the computation of that M. Now if that is not possible, then we are operating in the position domain where we are computing an error and then driving the error to 0 using servo control. Okay, so basically what we'll be talking about our control system when we say PD, PID control, it's basically position control of what? Position control of the joints, to take the manipulator from a present position to a desired position. And a couple of terms: single input, single output, independent joint control. Okay, and there is another term which we'll have to come to, which is called stable. So we'll come to stability as we go along. Now we said that this is a linear control system, so we're making the assumption that the system can be represented by linear differential equations. Okay, now all the links which are like this, okay, they have mass, they have some stiffness, and they have some damping, which is P. Okay, so the joint is going to have some friction, which is my damping. The link will have some stiffness, which is K, and M is the mass of the link. So each of these joints have some mass, spring, and damping associated. So for each of the joints, we represent this by an MBK system. Now, why by an MBK system? Because we understand the behavior of this MBK system very well. Now you would have studied this in right from high school. Okay, this is my M, B, and K, M, B, and K system. Okay, so each of the joints are represented this way by a M, B, and K system, and this is my present position, which is X. Okay, now so you can see that what we are saying is that we are modeling this. So I can simply model this as in terms of a rotating joint, it will be J, it will be K, and it will be B. Okay, in the case of a linear system, it will be MBK. Okay, they are equivalent to each other. Okay, so now the equation of motion of this system is given by the equation of motion is given by mx double dot plus bx dot plus kx is equal to 0. Now we know how to do that. You can draw the free body diagram, then find what are the forces acting. So there will be an inertia force, there will be an inertia force, then there is a damping force or friction force, and then there is the stiffness, which is my spring. Okay, spring force. Okay, so by drawing the free body diagram, we can find the equation of motion, and the equation of motion comes out like this. So mass into acceleration plus the damping, B into x dot plus kx is equal to 0. Okay, now this is a second order linear constant coefficient differential equation. So this is a second order differential equation. Okay, and we can solve this as a function of time. We can solve in terms of time as xt. Okay, this specifies the motion of the block, and the solution will depend on with initial conditions. which means that if I give a small force here and I leave it, how this is going to behave can be found by solving this differential equation with initial conditions. Okay, now this is a differential equation, so if I want to solve it and I want to find xt, then what we can do is we can take the Laplace transform of this. This is in the time domain, so I can take the Laplace transform and convert it to the S domain. Okay, so I can take the Laplace transform, it becomes ms squared plus bs plus k is equal to 0. Okay, this is in the S domain, and this is called the characteristic equation. Okay, now why is this called the characteristic equation? Let me just explain it here. So this is my mass spring and damper system. Okay, I'm going to give a small force F, and I want to know how this is going to be. If, for example, if I give a force and I leave it, whether it is going to oscillate, it will come and stop, or it will keep oscillating indefinitely. Okay, now the characteristic equation is the one, or the roots of the characteristic equation is the one that determines how it is going to behave. So if I write this, if I draw the free body of this and write as F is equal to mx double dot plus bx dot plus kx. Okay, this is the equation with the force. Now if I take the Laplace transform of this, okay, Laplace transform of this, then fs is equal to m into s squared xs plus b into s into xs plus k into xs. So fs is my input, and output is what? Xs. So this becomes xs into ms squared plus bs plus k. Okay, so I can write this as xs by fs is equal to 1 by ms squared plus bs plus k, and this is my characteristic equation. The same equation that we just looked there. So this is actually, if you look, this is an output by input relation. Okay, and this is also called the transfer function. This is also called the transfer function. So the characteristic equation actually determines how the system is going to behave. Okay, now the roots of the characteristic equation, if I have my characteristic equation, which is mx squared plus bs plus k is equal to 0. Now the roots of this determine the solution of the differential equation. Right? Now what are the roots of this equation? This is a second order equation, right? So the roots, it will have two roots, s1 and s2. So s1 and s2, what will this be? Minus b by 2m plus minus root over b squared minus 4mk divided by 2m. Okay, now we know this, you must have studied in high school. Now this has two roots, s1 and s2. Okay, now depending on s1 and s2, it is going to behave in a particular way. What do you mean by behave in a particular way? So I have, let me say this, my time axis is my x-axis. So if I take the system, I give it a small force and I move the mass till here. So I have my mass spring damper here. That's my mass spring and damper. Okay, so if I force it like this, I give a force, displace it to some distance, and if I leave it, okay, I'm displacing it to here now. Okay, from here I've gone here, I displace it and I leave it. Okay, how is it going to behave? So this is my x-axis, I displace it till here. So how it is going to behave means whether it will come back like this and here, whether it is going to oscillate a little bit and come back here, or it will keep oscillating a lot here. So this is what we mean by the behavior of the system. Okay, now how it is going to behave would depend on the roots of this equation, depending on s1 and s2. Now here we find that b squared minus 4mk comes under the square root. So essentially the behavior of the system would depend on that b squared minus 4mk. Okay, so this is my b squared minus 4mk. So depending on real and unequal roots, would mean that b squared is greater than 4mk. Okay, so in this if it's a real and unequal roots, b square is greater than 4mk. This is an overdamped system. Okay, this is overdamped. So it basically means that this is my this is the way it is going to behave. It's overdamped. Okay, which means b squared is greater than 4mk. Basically, physically means that your damping is so high that the spring cannot give back the energy to move the mass. Okay, so it is coming very sluggishly and coming to stop. Second is if the roots are complex or if they are imaginary. So complex roots means that b squared is less than 4mk, and this means behavior of oscillating kind of behavior or underdamped behavior, okay, which is equal to this one. So this is my 2. Now the third case is if b squared, so we have real and unequal roots, you have complex roots, and you have real and equal roots. The third case is real and equal roots, okay, which means b squared is equal to 4mk. Okay, now b squared is equal to 4mk means critical, okay, which is this one, critical damping. Okay, so depending on these 3 conditions, why 3 conditions? Because b squared minus 4mk, these are the 3 possibilities, right? So b squared is greater than 4mk, less than 4mk, or equal to 4mk, and based on this you get these 3 kinds of behavior. This is what we mean by behavior of the system, right? So what we basically in robotics look for is this critical damping. So in most of our cases we'll be saying b squared is equal to 4mk. We want this kind of behavior. A couple of important points to note here, which you have done this in high school, but I'm not sure if you ever noticed, if you never noticed this or you have asked yourself these questions. So mx double dot plus bx dot plus kx is equal to 0. The question is, can mbk be negative? Okay, now m is mass, so obviously it can't be negative. Okay, so m is mass, so it has to be positive. Okay, now what about b? So minus b means that, what is b? B is damping. So minus b means energy is being given to the system. Plus b means friction, right? Friction takes away energy, right? So plus b means friction takes away energy, right? So friction is basically taking away the energy that is being given to the system. What is the energy that is coming to the system? So when we are giving this force here and we are pushing it, we are basically giving energy to the system. So what is b doing? B is friction, so it's taking away the energy, okay, in terms of heat or plastic deformation. What is spring doing? Spring is absorbing the energy and then it's giving it back. M is inertia, so overcome the inertia forces that energy is being used. Okay, so if you look at this equation and try to think if mbk can be negative, m cannot be negative because it's a mass. B also cannot be negative because if b is negative, it means friction is helping the motion, which is not true. You know that friction doesn't help, friction impedes. What about k? K can be negative. Okay, k negative means opposing spring. What this means is F is equal to k into del x. So if I'm giving a force, the spring is compressing. Now if minus k is there, it basically means if I'm giving a k, the spring is expanding. That may be possible in cases of multiple arrangements of springs. Okay, so this is something, please think about it. Now in terms of stability, stability basically means that if we give a disturbance, okay, which is an energy, then the system remains near the origin. Okay, so if this is my origin, a system is here. If I give a disturbance, it basically means that it roams around, can go out like this, roams around here and comes back here. It may not come back exactly there, it comes somewhere near there. So this system is stable, whereas if I look at a system like this, okay, so if I give it a disturbance, okay, it goes out somewhere else. Okay, this is unstable. So this is stable, this is unstable. In the case of the spring mass damper system, this is my mass, this is spring, That's my damper. Okay, so in this particular case, if I give a disturbance f, okay, what would happen is, and if I leave it, it will come back to somewhere near x. Okay, so it will oscillate like this, and depending on the values of mb and k, but it will come back somewhere near x, near where it started, or near origin, what we call origin. Okay, such systems are stable. Now the other question which I wanted to ask, I don't know if you ever thought about it, is you would have drawn this graph, you would have seen this graph in many textbooks. Okay, talking about the stability, talking about the response of a system, the behavior of a system. Will there be some difference there, or this line will come and join the origin, not the x-axis? Similarly here, will there be some difference there, or it is going to come and join the x-axis? Please think about it. Okay, so what I mean is, will this come and join this at the end of the day? After as time goes to infinity, will it come and join, or there'll always be some difference there? Now, if you think a little bit on the physical system, when I'm giving an energy, the mass is moving. Okay, now where is this energy going? Some of the energy is getting consumed by B, damping. Now, if the energy is getting consumed, okay, it cannot come back to exactly where it was, because some energy has been lost. So energy is lost. So if energy is lost, it will not come back. So there will be some difference there. Okay, there will be some very small epsilon there. That is because of this energy being lost. Okay, so these are very small points, but please note. Now, in terms of stability, it basically means that in terms of stability, okay, S1 and S2 have to be negative. If it is negative, then we say it is stable. Okay, we'll come to stability later, but just note that they are all related. So characteristic equation gives us the solution. We need to find the solution of the characteristic equation to get the motion. For example, let's take this example of real and unequal roots. Okay, so in the case of real and unequal roots, we can solve this equation as x, the solution of the differential equation mx double dot plus bx dot plus kx is equal to 0. So the solution of this will be of the form c1 e raised to s1t plus c2 e raised to s2t. Okay, this will be the solution of this, and s1 and s2 are the roots of the equation. Okay, ms squared plus bs plus k is equal to 0. Okay, and the response of the system, if I look at the response of the system, the roots, where are the two roots going to be? Roots are going to be negative, because m, b, k are positive, so the roots will be negative. So there will be s1 and s2, which are on negative on the left side of the imaginary axis, and this is my real axis. Okay, and the response of the system, if I give it a disturbance xt, what will happen is it will come down like this. Okay, so this is a real and unequal root. So it's what kind of a system is this? This is an overdamped system, so it will come like this and stop here. Okay, so from this equation, from the equation of motion, we can find the characteristic equation. From the characteristic equation, we can find the roots. Okay, and depending on the roots, whether they're real and equal, real and unequal, and or complex roots, we will get a particular kind of response. Okay, so you can solve the equation with initial conditions. Okay, so this basically tells us that when we give an input to the motor and the link moves, okay, how it is going to behave, because the link that we have said is being modeled as a spring mass damper system, and it has a mass, the link has a mass, it has stiffness, and it has some damping. So how it is going to behave would depend on the values of m, b, and k. It is going to behave based on these values. Okay, so this gives us the very basic idea that we are using the spring mass damper system to model the motion of a link. Okay, and then we can choose, depending on the values of mbk, we can choose what kind of behavior it has out of these three, and we have said that we choose the behavior that the system should be should be critically damped. It should be real and unequal always. Okay, so this is critical damping, and we always consider this condition. Okay, so much about the behavior of this system. Now so far we did not put a forcing function. So basically we said that we are going to push the mass and we are going to leave it. Okay, so now suppose we want to control the position of suppose that we want to control the position of this mass. Okay, suppose I'm going to give a push and I'm going to leave the mass, but it doesn't go to the position that I want it to go. Okay, in that case, suppose that natural response, what we did is a natural response, because f was equal to 0. Suppose the natural response of our system is not what we want it to be. Okay, in that case, what we can do is with the use of sensors, an actuator and a control system, we can modify the system behavior and make it as desired. So we have the natural response of the system, and we don't like the natural response of the system, so we can add what we call sensors. Okay, then we can add an actuator and a controller, okay, to get my desired response. Okay, so sensors, actuators we have already studied. So position sensor like an encoder can be put, actuator like a motor, DC motor can be put, and then we have a controller. By putting all this, we can get a desired response. Okay, so now what we are saying is that M and F I'm going to put here now, and this is my M, B and K remains the same. This is B and that's K. Now because there is an F, I draw the free body diagram and it becomes mx double dot plus px dot plus kx is equal to F. Okay, so the question comes, what should be the suitable input to get a desired behavior? So in terms of control system, we need to find what is a suitable input of F to get a desired behavior. Okay, so that is the question. Now we did not like the natural response of the system. Okay, so we are putting a forcing function F, and I have to decide how much F to give so that we get a desired behavior of the system. Now this is basically called a position regulator. System or position regulator controller, in which we are simply attempting to maintain the position of the block. So a position regulator basically maintains the position of the block. This is not trajectory following. So if I want the end effector to follow a trajectory, that is a trajectory following controller. We'll come to that as we go along. This is only taking it from one position and keeping it in another position. This is called a position regulator. And the question is, how much F to apply? Okay, so this is what we mean by the designing a control system. Now in this position regulator, so we have seen our mx double dot plus px dot plus kx is equal to F. The question is how much F to apply. Okay, now let's try and figure this out logically. So this is M, this is B, and that is K. So this is an M, B, K. Sorry, this is my K. So this M, B, and K system. This is my F. Now, how much F should be applied? How do you answer that question? Now, suppose I am here at X and I want to go very far. I want to go to X dashed. So I basically want X to go to X dashed. Now, if this is very far, then I have to apply more F, more force. It's like saying that if you keep a mass on a table, okay, if you want the mass to go for a very small distance, I just want it to go here, then you apply a small F. If you want the mass to go very far, okay, you want the mass to go far here, and from here to here you apply a larger force. Okay, so if this is my F1, this is my F2, then F2 must be greater than F1, obviously, because the mass is going further distance. So F is proportional to the distance x that you are traveling. What is x? X is this distance. Okay, which is logical. Then if you have to travel more distance for the mass, then it needs more force. Okay, so F is proportional to, so F is equal to K into P into X. This we call the proportional gain. Okay, so this Kp is called my proportional gain. Okay, this is called the proportional gain. Now, something that is going to happen here is the mass also has a spring. So that's a mass and that's a spring. Okay, so if I give a force and I take it till here, okay, and then if I leave it, what is the spring doing? The spring is absorbing the energy and giving back the energy. Okay, so what is going to happen is if I push it and I leave it till here, it will if it has to come back to the original position x, it will first travel this side, then the spring will push it back, it will go this side, and then it will come this side again. It will oscillate about that point. Okay, now that is what the spring does. Now suppose I want this mass to move. I'm giving an F here. I want this mass to move to this point here. This is my distance x. Suppose this is the distance up to which I want it to move, and I'm giving a force which is equal to Kp into x. Now what will happen is when the mass reaches this position, if you can imagine, the mass has reached this position, it has inertia, that is m into x double dot. Now because of the inertia, it will not stop here, it cannot stop. Okay, so it will cross across and go on the other side, it will go this side now. Once it goes this side, the spring will push it back now. Okay, because what has happened, my x has become minus, on this side x is minus, so the force is reversing, it is coming this side now. So I'll say that again. There is a mass here and I want it to go from x to x dash. Let me draw it again. So I want this mass to go till here. This is my point x. Okay, so what happened is this force that I'm applying is equal to Kp into x. It's a constant force. So the mass starts moving, and then when it reaches this position here, it cannot stop because of this inertia. It will cross over and go that side now. Now the moment it goes that side, what has happened? X has become negative now. If x becomes negative, the force will tend to push it on the other side now. Okay, so it will tend to come back this side. Okay, so I'm pushing the mass back again, so it has come here. Now again what has happened is that it will not stop exactly at that desired position because of inertia, so it will cross this side. So what will happen? You'll get oscillation about that point. Okay, so it is not being able to stop because of inertia, so we need to add another term. So the force must be proportional to x, which is okay, but it should also be proportional to x dot, the velocity, which is the incremental velocity, which is the difference between the point I want to go and where I am. Okay, so as you're coming nearer and nearer to 0, your force should decrease. Then it will go and stop at that. I hope you can imagine that point. You can imagine that if this is the mass and that's the desired position, as it is coming nearer to that, which is x dot, it should the force should decrease. Then it will go and stop here. Okay, so we need another term which is proportional to x dot, and this is equal to kd, or in some places it is called kd or kv into x dot, where kv is called my derivative gain. Okay, so kp is the proportional gain and this is called the derivative gain. Okay, now so we have the force that we are applying is proportional to two things. One is the proportional gain and the other is the derivative gain. So force is equal to kp into x plus kv into x dot. That's the force. So what I will do is I'll put this force equal to this plus this, and I want to bring it on the left side, so I can write this as minus. So F is equal to minus kp into x minus kv into x dot. Okay, I hope you understand where this came from and where this came from and what is the logic in that. So if I take this F and put it into that equation there now, okay, what will we get? mx double dot plus bx dot plus kx is equal to minus kp into x minus kv into x dot. Okay, and if I bring mx double dot plus x dot into b plus kv plus x into k plus kp is equal to 0. Now I can write this as m into x double dot plus x into k dashed, sorry, x into b dashed plus x into k dashed is equal to 0. Now this is equal to b dashed and this is equal to k dashed. Okay, now this equation, why are we bringing it in this form? Because if you look at the form of this equation is exactly of the same form. This is equal to this form. Okay, so what we talked about when we started talking, this is in this form only, isn't it? It is mx double dot plus bs plus k, sorry, bx dot into kx is equal to 0. Okay, so it is in this form only, right? So if it is in that form, basically it can behave in only these three ways, and we know that we want critical damping behavior. So by putting b square is equal to 4mk, I can actually design the controller such that I can choose the values of kv and kd, kp and kv, such that b square is equal to 4mk. It behaves in a critical damped way. Okay, so now I hope you understand why we did it like this and why there was emphasis on that equation, this equation that we started off with. So now k dashed is also called the closed loop stiffness. Okay, now so this is one equation with two unknowns. So in for a physical system, m is mass, b is friction, and k is spring. This will be known. So in this one equation, what is not what is unknown? What is unknown is kv and kp. Okay, so kp and kv have to be found out, and they determine the response of the system. Okay, so let's do a very simple example in which we are given the parameters of a system. Let's take a very simple example. The parameters of a system are m is equal to 2, b is equal to 2, and k is equal to 2. Now for kp equal to 16, okay, the system is critically damped. So what we are asked to find is the closed loop stiffness and the corresponding kV. So we are asked to find closed loop stiffness and corresponding kV. Okay, so something again, I just go back and emphasize here. So we have one equation here. This is one equation, right? So this is one equation. Okay, now in this one equation, m is known, b is known, and k is known. These are system parameters. Now the controller has a kp and a kv. So this is basically called a proportional derivative controller, or PD controller. Okay, proportional plus derivative controller. So this is called the proportional gain, and that is called the derivative gain. Now if I want to find the values of kp and kv, because I have one equation with two unknowns, you cannot find them exactly. Okay, so we basically need two conditions. One is I assume closed loop stiffness, which means b squared, b dash squared is equal to 4m k dashed. So there is a critically damped one condition. Another condition is I'll need the value of either kp or kd. Okay, otherwise I cannot solve this equation. Okay, so there is nothing like what is the exact value of kp and kd. You can't find an exact value because you have only one equation with two unknowns. So you can assume one of the unknowns. In this particular case, we have assumed that, or we are given that kp is 16 and the system is critically damped. So we have two conditions. Now I can solve. Okay, so I hope you understand that there is nothing like an exact value of kp and kd because you have one equation with two unknowns. Okay, so here what we are seeing is that we are given, let us go back again to that equation that we wrote, mx double dot plus p plus kv into x dot plus k plus kp is equal to 0. Okay, so what are we given? We are given m, b, k, and we are also given kp. We are given kp. Okay, and for critical damping, we know that b dash squared is equal to 4mk. Okay, so we are given, so m is equal to b is equal to k is equal to 2. We are given. What else is given? kp is equal to 16. Okay, kp is equal to 16. This we are given. All right, and we are given critical damping, so b dash squared is equal to 4mk dashed. These conditions we are given, right? So from here we can find what is k dash. K dashed is equal to, what is k dash? This is my k dash, that's the b dashed. So k dashed is equal to k plus kp, which is equal to 18, and b dash squared is equal to 4mk dashed. So b dashed is equal to 2 root m k dashed, okay, which is equal to 2 root 2 into 18, which comes out to become equal to 12, and kv is equal to b dash minus b, which is equal to 12 minus 2 is equal to 10. Okay, so I found the values of kp is already given. Kp is already given. We have found the values of kv also. Now we were given kp equal to 16, so I have to find the response of the system. How do you find the response of the system? Put in these values into this equation, okay, and then find the solution of the differential equation xt, okay, and plot it with respect to time. So now if the response, let's say my system is like this, okay, and I want the behavior of the system. Suppose it is doing something like this, okay, there's too much overshoot that is coming here, then I need to decrease kp. So there is nothing like an exact solution, so nothing like exact solution for kp and kv. Okay, you have to actually put values of kp, assume numerical values, look at the response. Now if there is too much overshoot, then you reduce kp. If there is less overshoot, say for example if the system is coming like this, system has come like this and it's come like this, then you can increase kp. Okay, so and this is basically what we call by tuning of the controller. So we tune the controller such that we get a particular response, and after we get the particular response, if you're satisfied with it, that's great. If it's not satisfied, then you change the value of kp again. So there is no exact way of by saying that what is the exact number or what is an optimal number of kp or kv. There is nothing like that. You just have to experimentally try by putting different values of kp and then looking at the response of the system and then deciding whether it is okay or it is not okay. If it is okay, then it's great. If it's not okay, then you change it. Okay, now the issue with this kind of control system, so this is basically a PD controller. We talked about a PD controller or proportional and derivative controller. Okay, so now what we do see is that this is basically based on the servo part, but now we have seen that there can be errors in estimating m, the inertia parameters. There can be other errors in the system. Okay, so what we might need to do is that this control system may not work very well, because if there are errors in that m estimation of m theta, then there are errors in the system now. So what we can do is we can divide or we can partition the control system into model part, which contains the m, b and k parameters, and servo part, which is basically servoing and reducing the error, which is causing the error to go to 0. So such control systems are basically called partition control systems, in which we partition the control system such that and how do we partition the control system? So we partition the control system by assuming mx double dot plus bx dot plus kx is equal to f, and this f is equal to alpha into f dash plus beta, and we say alpha is equal to m and beta is equal to bx dot plus kx. Okay, so if I take this bx dot plus kx, so if I take this and I take this value of alpha and beta and put into this equation, what we do get is mx double dot plus bx dot plus kx is equal to alpha is equal to m into f dashed plus bx dot plus kx. Okay, so now if you see, this cancels, this will cancel with this, and this will cancel with that, and what we are left with is x double dot is equal to f dashed. Okay, this is basically called a partition control system. This is also called control of a unit mass system. Okay, it is like we are controlling a unit mass. So x double dot is equal to f dashed, okay, is the control of a unit mass because it's like 1 in 2 acceleration. Okay, and this kind of control systems are called partition control systems, which are very useful for robotics applications, and we'll look at this in the next class, and we'll see that this kind of control system can also take care of nonlinear systems. So in the next class, we'll be looking at the partition control system, and we'll be seeing that the partition control system can also take care of nonlinear systems. Okay, and this is required because the model part can have errors. There can be variations in estimation of mass, in computation of Coriolis centrifugal forces. So the concept of partition control system will continue in the next class. So we'll stop here today. Thank you.